Hi, I'm Marissa.
And I'm Austin. We're both seniors in Biomedical Engineering Society at UW-Madison. Today, we would like to show you some of the things that we study every day.
There are many things that you can do as an engineer. Personally, we study how you can apply engineering principles to the world of medicine and biology. In other words, we look for ways to improve or replace something in your body that stops working like it should. We, as future BMEs, apply science and technology to develop new tools like helping people who can't walk walk again.
Biomechanics is a field within biomedical engineering that looks at the science behind how we move. When you walk, for example, your muscles, bones, and tendons work together every step of the way. You have three types of muscle within your body. Cardiac muscle is what your heart is made of. Smooth muscle is what other organs in your body is made of, like your stomach. These are muscles that move without you having to think about it. Alternatively, skeletal muscle is used for voluntary movements such as picking up a water bottle or standing up from your chair.
40% of your body mass is skeletal muscle, so a lot of engineers study how this type of muscle works. For example, when you go to pick up a pencil, do you think about how to move each muscle as you go to grab it? Most people would say that they're able to just pick up the pencil without a second thought. So, what steps do you think your body takes when you go to pick up a pencil?
So, what steps do you guys think your body takes when you go to pick up a pencil? Is it A, your muscles act by themselves with no signals? B, your heart tells your muscles to move? C, electric signals start in your brain and travel to the muscle? Or D, magic? I know you guys would think the correct answer is D, but it's actually C. Electric signals start in your brain and travel to the muscle.
Your body is able to move thanks to skeletal muscle, which is activated through the use of electrical signals that come from your brain. Your brain sends these signals all the way from your head down to the muscle that you need to move through nerves. Nerves act as an electrical connection between the brain and every single skeletal muscle in your body, and they do this in less than a second.
Today, we'll show you how you can make your skeletal muscle move by applying electricity. The electricity we are applying will act like the electrical signals sent from our brain to our muscles when we want to move. This device sends electricity through these wires to a muscle for us in your calf called your gastrocnemius. The electrical signal makes your muscles contract and therefore you're able to move.
In this demonstration, we will be applying small amounts of electricity to our subject's muscle, causing it to activate and contract. It is important to note that this experiment in no way harms the subject and is similar to simply flexing a muscle repeatedly. We will be stimulating the gastrocnemius, commonly called the gastroc, which is the largest muscle in your calf. If you stand on your toes, you should be able to see this muscle appear on the top portion of your lower back leg. This muscle is responsible for generating much of the force needed to do things like climb stairs or jump in the air. The first step of this experiment is to sanitize the skin over the muscle you want to stimulate. This will allow for the best possible contact and create a clean surface for the experiment. Next, we will place an electrode on the upper portion of the gastroc muscle. An electrode is a medical device that allows the electricity to transfer from the device to the body. The side of the electrode placed on the subject has an adhesive so it stays in place throughout the experiment. The device, or electrical stimulator, has both a negative and positive electrode. The first one that was placed was the negative electrode, and this one is the positive. Once both electrodes have been placed on the muscle and are secure, we are ready to begin stimulating the muscle. As you can see now, we are programming the electrical stimulator to apply a specific amount of electricity over specific amounts of time. We will apply a very small voltage to the muscle every 2 seconds, and when that occurs, you will begin to see the muscle twitch. The subject is asked to remain still and relax so the only source of stimulation to the muscle is from the device. If you watch closely, you can begin to see the subject's muscle moving. The power of the electrical signal is very slowly increased until a noticeable physical response occurs. The electricity we are applying to the gastroc is similar to the electrical signals it would receive from your brain when you want to activate your calf. Therefore, the muscle responds to the signal and contracts, which results in the twitch we see throughout this experiment. Here's a graph of the electrical signals your calf muscle receives. These peaks represent when your muscle twitches. We can also increase the frequency of the signal, as seen here. The larger the frequency, the more your muscle moves and the greater the peak.
Biomechanical engineers study how your muscles work so they can try to fix them if they stop working. Biomechanical engineers also study human movement patterns to help those who suffer from injuries or who have physical disabilities. Specifically, some biomechanical engineers closely study the movements of athletes to help them train to run faster, throw further, and jump higher in whatever sport they participate in.
If you guys thought this video was cool, we encourage you to stick around for an activity that you can do at home. And we hope to see you guys on campus someday as future Badger engineers.
For today's activity, we will be making a robotic hand out of cardboard. Pause here for written instructions and materials. For this activity, you will need a piece of cardboard, a ruler, tape, scissors, 5 10-inch pieces of string or yarn, a pen or pencil, and 2 to 3 straws. Begin by tracing an outline of your hand onto the cardboard. Next, cut out your hand outline. Cut the straws into 9 1/2-inch pieces and 5 1.5 to 2-inch pieces. Depending on the size of your hand, you might have to make these pieces smaller. Tape these pieces onto the cardboard hand as shown. Repeat for the other fingers. Notice that for your thumb, you only need 1 short piece and 1 long piece, while the other fingers have 2 short pieces and 1 long piece. Next, take a piece of string and string it through the top straw. Tape the tip of the string to the back of the cardboard to keep it in place, then continue stringing it through. Do this for all the fingers, making sure to only have 1 string per finger. Crease the cardboard in between the straws. This will simulate your joints. Pull on each of the strings or pull them together to see how our hand moves. Believe it or not, we have no muscles in our fingers. Instead, we move them by tendons, which act like the strings on our cardboard hand. Tendons link the bone in our fingers to the muscles in our arm. When we flex our fingers, our muscles pull on our tendons like you are pulling on the string. Thank you for watching. We hope you enjoyed our video and learned more about what it means to be a biomechanics major here at UW-Madison.